In this video, we are going to look into aromatic diazonium salts, into their preparation and their reactions. In the previous videos, you have seen that electrophilic aromatic substitution is a common reaction of benzene ring or aromatic compounds. Of course, in those cases, reagents are electrophiles. Another large class of reagents are nucleophiles, and it would be advantageous for us to be able to carry out also nucleophilic aromatic substitution. One way to do that is to carry out reaction on diazonium salts of aromatic compounds. So in such reaction, diazonium group is replaced by a nucleophile. And so here is general scheme for such reaction. Diazonium group is shown here. So it's N2 group where two nitrogen atoms are bonded by a triple bond. Nitrogen atom attached to benzene ring carries formal positive charge, and of course such compounds are salts and they have to be accompanied by corresponding counter ion, corresponding anion. Diazonium salts readily react with nucleophiles, and nucleophile displaces diazonium group. Byproduct is molecule of nitrogen, gas that bubbles out of the solution. Nitrogen, of course, is very stable gas, very stable compound, and that makes this process thermodynamically favorable. Diazonium salts are prepared in diazotation reactions. Diazotation reaction involves reaction of amino group, so simplest compound will be aniline. So reaction of amino group with nitrous acid. But nitrous acid itself is unstable. It cannot be prepared and isolated. Instead, we prepare nitrous acid in situ. In situ means in the reaction mixture. So nitrous acid is prepared from nitrites, salts of nitrous acid. The most common, the most readily available nitrate is sodium nitrite. So we use sodium nitrite and add strong acid such as hydrochloric acid, so aqueous solution of hydrogen chloride, hydrochloric acid, and we carry out reaction in an ice bath. So reaction of sodium nitrite with hydrochloric acid produces nitrous acid. Left standing on its own, nitrous acid would decompose in a short period of time. But we carry out reaction in ice bath, so that slows down decomposition of nitrous acid, and as it is formed, it reacts with amino group to give corresponding diazonium salt. Diazonium salts readily undergo substitution reactions with nucleophiles to give corresponding substitute products. This is one way to introduce nucleophile on benzene ring, and that reaction is called Sandmeyer reaction. So here is one example, introduction of bromide nucleophile. So first, in the first step, we prepare diazonium salt. In this case, because we want to introduce bromide as a nucleophile, we should use aqueous solution of hydrobromic acid, not hydrochloric. We introduce bromide anion as counter ion, so that when we treat the resulting diazonium salt with copper bromide, which is source of bromide nucleophile, there is no competition with chloride nucleophile. If we had prepared benzene diazonium chloride and then treated that with copper bromide, then you would have presence of chloride and bromide nucleophiles, and there could be exchange of nucleophiles and scrambling of the two of them, and we would end up with mixture of chloro and bromobenzenes. So to avoid preparing such mixtures or formation of such mixtures, we have to be consistent and make sure that nucleophile is the same. So we treat benzene diazonium bromide with copper bromide as a source of bromide nucleophile to prepare bromobenzene. Of course, to prepare chlorobenzene, we'll use corresponding copper salt, copper chloride. Typically, we indicate copper chloride as CuCl, but actual formula is Cu2Cl2. So both are in use, simplified formula or the actual formula. To prepare iodides, we can use potassium iodide as a nucleophile, and because iodide anion is such a strong nucleophile, much stronger than bromide or chloride, we can prepare benzene diazonium chloride and treat that with potassium iodide. There won't be competition because iodide nucleophile is much stronger than chloride, and so there won't be competition from chloride nucleophile. Product is iodobenzene. So these are methods to prepare chlorobromo or iodobenzenes. These are all compounds, products that we could have also prepared in electrophilic aromatic substitutions. So this is a method of choice, but we could have prepared it in different way. As you may recall, we cannot prepare fluorobenzene in an electrophilic aromatic substitution. Well, we can do so in Schumann reaction. Schumann reaction is a variation of Sandmeyer reaction where we prepare fluorobenzenes. So to prepare fluorobenzene, we first need to prepare benzene diazonium salt. But now we cannot have bromide or chloride as nucleophiles because we don't want them competing with fluoride nucleophile. We cannot use hydrofluoric acid because it's weak acid, so we cannot use that in preparation of nitrous acid because it's weak acid and it would not displace nitrous acid from its salt. So it would not react with sodium nitrite to give nitrous acid. We have to use strong acid that contains fluoride nucleophile, and that's tetrafluoroboric acid, HbF4. So we treat sodium nitrite with tetrafluoroboric acid in ice bath, and then we obtain as product benzene diazonium tetrafluoroborate. Tetrafluoroborate anion is source of fluoride nucleophile, and upon heating it will result in formation of fluorobenzene. So that's one way to carry out Schumann reaction or preparation of fluorobenzene. Another is to prepare actually diazonium salt as usual, and so we have chloride nucleophile and then treat that with excess of tetrafluoroboric acid and heat, and that could also give us fluorobenzene. First method is preferred because product is cleaner. We can make sure that there is no competition with preparation of chlorobenzene. Finally, we can use other nucleophiles in this reaction, in Sandmeyer reaction, not just halogen nucleophiles. Here is an example. So if you use cyanide nucleophile, nitrile nucleophile, or cyanide anion, if this is inorganic salts, then it's cyanide. We use copper cyanide. You have noticed copper salts are best sources of nucleophiles for this reaction. And then product is benzonitrile. One important nucleophile, of course, is oxygen. And we can react benzene diazonium salts with oxygen nucleophiles to produce corresponding oxygen-containing compounds. For example, reaction with water upon heating will replace diazonium group with hydroxyl group, and product is phenol. Now, for better yields, actually we should use copper salts. So reaction works much better, proceeds cleaner. That means one product is obtained, and in better yield, if we add copper oxide, copper 1 oxide and copper nitrate, mixture of copper 1 oxide and copper nitrate, then reaction proceeds at room temperature, and water as a nucleophile displaces diazonium group to give phenol. Sometimes we exploit a reaction like this in a sequence of reactions that will introduce desired nucleophile in particular position. So here is an example of rather lengthy reaction sequence to prepare metabromophenol. So you know that phenol with hydroxyl group reacts with electrophilic aromatic substitutions to give ortho and para substitute products. It's very difficult to introduce new substituent in meta position. So in this case, we can start, for example, on the left with nitrobenzene, very easy to prepare from nitration of benzene. And then if we carry out bromination of that substrate, we end up with meta-bromonitrobenzene. Obviously, nitro group is meta-directing, so we end up with meta-bromonitrobenzene. Now, catalytic hydrogenation results in reduction of nitro group to amino group. So meta-bromonitrobenzene is converted into meta-bromoaniline. And then diazotation reaction converts meta-bromoaniline in meta-bromobenzene diazonium chloride. And then replacement of diazonium group with water with oxygen nucleophile results in formation of desired product, metabromophenol. So as you can see, rather lengthy procedure, but in a sequence of reactions like this, we can pretty much prepare any aromatic compound we want with any substituents in any positions relative to each other that we want. Finally, one important reaction of diazonium salts is replacement by hydrogen. At first glance, that may appear to be undesired reaction. Why would we want to do that? Because displacement of benzene diazonium salt with hydrogen results in formation of benzene. Well, benzene is readily available, inexpensive compound, and formation of diazonium salts is difficult or more difficult and results in increased value compound. So why would we want to convert more expensive, more valuable compound into something less expensive? Well, we don't, but in preparation of more complex substrates, sometimes it's advantageous to exploit diazonium substituent to introduce new groups and then remove it, get rid of it. So let's say we want to prepare 1,3,5-tribromobenzene. Well, bromine is ortho-para directing. As soon as we introduce one bromine, it will direct new substituents ortho and para to itself. So that's very difficult to prepare. But if we have an auxiliary substituent, let's say amino group, so we start with aniline and carry out bromination of aniline, amino group as a strongly activating substituent will direct incoming substituents ortho and para to itself. So exhaustive bromination of aniline results in formation of 2,4,6-tribromoaniline. So now three bromines are 1,3,5 to each other in desired positions. The only thing is we have this amino group that we don't need. So we convert it in diazotation reaction, and you can see here sulfuric acid is used just to show versatility that we could use other acids, not just hydrochloric or hydrobromic. Any strong acid will do. So we convert it into diazonium salt, and then treatment of diazonium salt with hypophosphorous acid. So remember this reagent. That's hypophosphorous acid, H3PO2. Hypophosphorous acid has hydrogen directly attached to phosphorus. And actually there are two hydrogens that are directly attached to phosphorus in hypophosphorous acid. So one of those two hydrogens acts as a nucleophile. Reaction is actually a free radical reaction. So and displaces diazonium group. So hypophosphorous acid is reagent to displace diazonium group with hydrogen, and then product is desired molecule 1,3,5-tribromobenzene. There is another type of reactions of arene diazonium salts, benzene diazonium salts, where arene diazonium ion acts as an electrophile, as electron deficient species, and it reacts with nucleophiles. Reaction is diazocoupling reaction. In reactions like these, electron deficient nitrogen is not nitrogen that carries formal positive charge, it's nitrogen next to it. And that's because of the electron withdrawing effect of the nitrogen that carries positive charge, then terminal nitrogen is actually one that is electron deficient. So that's the one that will form a bond with a nucleophile. In this case, activated benzene ring acts as a nucleophile. So typically benzene ring that has strongly activating substituent acts as a nucleophile, and result is diazocoupling reaction. Products are azo compounds, so compounds that have nitrogen double bond and one substituent on each nitrogen. These compounds are brightly colored compounds and are often used as dyes, as paints. They have other uses, but that's one of their uses. So this particular compound shown in this example, reaction of benzene diazonium chloride with phenol, results in formation of an orange compound, orange dye. Azobenzenes could exist in form of two isomers, cis and trans. So obviously, if substituents are on the opposite sides of double bonds, that's trans, and same side, cis. Those are stable compounds, stable isomers, and they could be separated and isolated. Trans, of course, is stable form because cis suffers from steric hindrance. Substituents are on the same side. And here is the mechanism. So you can see from the mechanism why nucleophile has to be benzene ring with strongly activating substituent. Strongly activating substituent donates electron density to benzene ring, as you can see in ortho and para positions. Because para position is less hindered, its para-carbon of the benzene ring that forms a bond to the electrophile, to electron-deficient nitrogen. Once the bond is formed, we have intermediate, and base removes proton from para position of the intermediate to restore the aromatic ring, the aromatic benzene ring, and then once proton is removed, the final product is formed. Final product is azo salt. This particular azo salt is a yellow dye. If for any reason para position is blocked, obviously if substituent is in para position, then only then activated benzene ring will react in ortho position. This completes our study of preparation and reactions of aromatic diazonium salts, and next we are going to look into nucleophilic aromatic substitution.